All right, in our last video, we talked about the rules for exponents, depending on if we're adding, subtracting, multiplying, raising to a power, or dividing. Let's go ahead and now go through those a little bit more in detail and do a few more examples on those different rules. So we talked about multiplying. When I'm multiplying like bases and they have exponents, what we can really do is combine those bases by just adding the exponents. So for example, if we have a cubed, that's 3a's, and I have a squared, that's 2a's, how many a's do I really have altogether? Well, I have a to the fifth. So I can combine those as long as those bases are the same by adding the exponents. Here's another example. Students get a little bit confused when the bases aren't variables, but it would work the same way as long as your bases are the same. So if I have 3 cubed, that means I have 3 times 3 times 3, times 3 squared, that's another 3 times 3. I really have 3 to the fifth, right? I have 5 threes, and then I can do 3 times 3 times 3 times 3 times 3 and get 243. As long as your bases are the same, you should be able to combine them into one base by adding their exponents. Let's do a few examples here. Multiply and simplify. So in example number 1a, we have 2 cubed times 2 to the 8th. As long as my bases are the same, I should be able to smush them together and then just add their exponents, and I can say 2 to the 11th power. You could figure out what 2 times 2 times 2 11 different times is, or if you have a calculator, you can do 2 raised to the 11th power. You should end up getting 2048. So depending on how my math lab wants you to leave your final answer, you should be able to give them the answer in both forms. Look at example B. B says that we have 5 cubed, that's 3 fives. We have 5 to the 8th power, that's 8 fives. And then we have 5 to the, remember, if there is no exponent, there's an invisible 1. We have 1 5 there. Well, how many 5s, as long as they're the same base, do I really have? Well, if I add up all of their exponents, I really have 5 to the 12th power. Or I can do 5 to the 12th power, woo, and get a really large number. All right, let's look at these last couple. Let's throw some variables in there. And so look at example number 1c. I have this quantity r plus s to the 7th power. That means I have 7 of those. And I also have another r plus s to the 6th power. And remember, when those parentheses are next to each other, it means multiply. So I'm really just taking these like bases and I'm multiplying them together. Remember, as long as your bases are the same, you should be able to combine those and then just add their exponents. So I really have how many r plus s's? Well, I really have 13 of them. And so I can write it as r plus s. Remember, you have parentheses around it to the 13th power to represent that I actually have 13 of that whole thing. Okay? All right, look at D with me. D has the parentheses again next to each other, so it means I'm multiplying. Remember, I can only multiply and combine things with like bases, so you should be able to do your coefficients first. So I can do 2 times 4 and get 8. Then I can take all of the bases that have the same base, and really I can just add their exponents together. So if I have a cubed times another a cubed, I really have a to the 6th, right? I can do the b's. I have a b squared times a b to the 5th, which really means I have b to the 7th. Remember, a to the 6th and b to the 7th are not like bases, so I couldn't combine those in any other way. That would just be your final answer. Let's do another example with division here. So when I'm dividing like bases, what I can really just do is subtract their exponents. Let me show you a quick example of why that would be. Looking at this example, we have w to the 7th divided by w cubed. So w to the 7th really means that I have 7 different w's in my numerator. W cubed really means that I have 3 different w's in my denominator. Well, hopefully we know that if we have a factor of the top that's the same as a factor of the bottom, we can reduce both the numerator and the denominator by that amount. So if I have a w on the top and a w on the bottom, I can reduce them, cancel them out, right? And so I can do that again with my next w and then my third w. And so then how many w's do I really have left in my numerator? Well, I have 1, 2, 3, 4. So I could really say I have w to the 4th. Now, you can write it all out every single time, but when those exponents get really large, it's going to take you a lot of time and a lot of unnecessary work to write them all out and cancel or reduce. Instead, can't we just take 7 minus 3 and get w to the 4th? By subtracting our exponents. A little bit easier, right? All right, look at example number 2 with me. On example number 2, we're going to divide and simplify. Part A says we have 7 to the 9th power divided by 7 to the 4th power. Remember, as long as those bases are the same, we don't want to reduce these 7s. Be careful with that. That's a common mistake. What that really means is that we have 9 7s in our numerator. 1, 2, 3, 4, 5, 6, 7, 8. 9. And how many 7s do I have in my denominator? Well, I have 4 of those, right? And so we could reduce, reduce, reduce. And then how many 7s do I really have left? Did I reduce too many 7s at the top? There we go. How many 7s do I really have in my numerator? How many 7s do I have left? Well, I have 5 of them, right? And so my base stays the 7, and I have 5 of them remaining. And so it'd be 7 to the 5th power, not 1 to the 5th power. So be careful not to cross off your bases at the beginning. Okay? All right. Look at B. B says that I have 5a to the 12th power, that whole quantity raised to the 12th power. I have 12 of them. And then I have 5a to the 4th power. I have 4 of those in my denominator. If I'm dividing, what I could really do, as long as my bases are the same, is combine them into the same base and then just subtract their exponents. So what's 12 minus 4? 8, right? And so I have 5a to the 8th power. Now be careful. Please make sure that you continue to use your parentheses, because 5a to the 8th power written like this does not mean the same thing. On this one, the only thing that's raised to the 8th power is the a, where in this one we know, because it's in parentheses, that the 5 and the a are both raised to the 8th power. It makes a difference. So make sure you continue to use those parentheses, okay? All right, let's do a few more. If you look at example number 2C with me, we've got a couple of different things going on and a couple of different variables. So remember, they have to be like bases in order to be able to simplify or combine them. So let's start with our coefficients. Can I take -3 and divide it into 24? So it's 24 divided by -3. Did you get -8? So did I. All right, now let's do our x's. So if I have x cubed divided by x to the, remember there's an invisible 1 here, as long as they're the same bases, when I'm dividing, I should be able to just subtract my exponents, right? And so 3 minus 1 is 2, and I can say a simplified version would just be x squared. Do the same thing with your y's. Those are like bases. So if I have y to the 8th divided by y squared, I can really combine those into the same base and just subtract their exponents. So I got y to the 6th. Your final answer then should be -8 x squared y to the 6th. There's no other like term, so that would be it. Look at D. D is a little bit different because as you're looking at these coefficients here, they don't quite divide as evenly as example C did. But what I can still do when I have a fraction, 4 over 6, can I still simplify that a little bit by reducing? And so what number can be divided into 4 and into 6? I got 2. So I'm going to reduce the 4 by 2 and the 6 by 2 and really say that 4/6 is the same thing as a reduced version, 2/3, right? 2 on top, numerator, 3 on the bottom in the denominator. So now let's look at our other like bases. Let's look at our p's and our q's. If I have p to the 5th divided by p squared, because they're the same base, I should be able to combine them and just subtract their exponents. So 5 minus 2 is 3, so I end up with p to the 3rd power. Now be careful. Think about where that p cubed is. It should be in the numerator because the 2 p's from the bottom and the 2 p's from the top reduce. That leaves me with 3 p's in the top. So be careful not to write the p. Be careful not to write the p next to that 3 on the denominator. Please be careful to show that it's actually still in the numerator, okay? All right, same idea with the q's. I can combine those, and I have q to the 7th divided by q to the 1st. I can combine them by subtracting their exponent and get q to the 6th. So you can write the answer like this, or if you prefer, you can write the 2, the p cubed, and the q to the 6th all in the numerator. And in the denominator, I would still have just this 3. So both of these answers are the same version, as long as you're careful to clearly show what values are in the numerator versus in the denominator, okay? So far we've talked about adding and subtracting things with exponents where we do nothing, we combine like terms. We've talked about multiplying, where we add the exponents, and then we've talked about dividing, where we subtract the exponents. Why don't you do some practice problems on those type before we move into the next rules for exponents?